Okay, 3.3 and 3.4, we're going to take a look at that idea called the mole now, and we need a mole. We need this idea of a mole, of a big counting unit, because when we work with elements and molecules, we never work with individual elements or molecules. We work with a lot of them at once. So it's kind of like when you're ordering bakery, when you're ordering donuts. You know, you don't say I need 12 donuts. Instead, you say I need a dozen donuts. Or if you're ordering paper, you typically wouldn't say I need 500 sheets of paper. Instead, you would say I need a ream of paper, which equals 500. In the case of elements, we need to talk about a whole heck of a lot of them. So that's where the mole comes from. So what is it? It's defined as the number equal to the number of carbon atoms in exactly 12 grams of pure carbon-12. So we've got 12 grams of carbon, and each one of those carbon atoms would have 6 protons, 6 neutrons, and 6 electrons. The number, okay, what number is it? Well, it's 6.022 times 10 to the 23rd. So that's how many carbon-12 atoms are in 12 grams of that substance. Okay, so that's called Avogadro's number. Actually, not exactly thought of by Amedeo Avogadro, but named his number in memoriam to him. So 1 mole of carbon equals 6.02 times 10 to the 23rd carbon atoms. And that equals 12.01 grams. Now you may say, okay, wait a minute, Mr. Cornick, you said up here that it's 12 grams of pure carbon-12, and it's exactly 12 grams. And this certainly isn't exactly 12 grams. But please understand that this is not pure carbon-12. See, carbon atoms, if you had a handful of carbon atoms, maybe like charcoal, for instance, it's certainly not pure carbon-12. There's carbon-13 and very small amounts of carbon-14 inside of that coal that you're holding. So 1 mole of carbon atoms has that mass right there. And what you'll see if you look on the periodic table is that mass, 12.01, it's actually on the periodic table. And in our previous video, and with our lesson in class on Monday, we were saying 12.01 had a different unit associated with it. We said it was the atomic mass unit. Okay? But we also probably referenced that an atomic mass unit is kind of inconvenient because we don't have a scale that gives us atomic mass units. So hopefully with the activity in class on Monday, you understand the relationship between atomic mass units and grams. Alright, so let's take a look at a visual of 1 mole of stuff. Carbon in the upper left-hand corner, that would be 1 mole of carbon. Sulfur, those are pretty similar. Sulfur is a little bit more dense, actually, so it looks like they've got the same volume, but sulfur's got almost 2.5 times the mass. Mercury, doesn't look like very much mercury at all. That's the middle one, but you all know that mercury's pretty dense stuff, so we don't need a lot of it. Here's copper in the lower left-hand corner, and then iron in the lower right-hand corner. So each one of those things, each one of those samples contains about 1 mole of their respective atoms. So how many grams would that be? Well, for carbon, 12.01. We said that on the previous slide. Sulfur, 32.06. Mercury, 200.59. Copper, 63.55. And lastly, iron, 55.85. And you'll notice that those numbers I'm pulling right from the periodic table. Those are what we have called thus far as the mass numbers. So the mass number, we can make this relationship, we can say that the mass number on the periodic table is equal to 1 mole of that element's atoms. Alright, let's continue on then. Do a little concept check. Let's calculate the number of iron atoms in a 4.48 mole sample of iron. Alright, so here's what we'll do. We know that 1 mole, we abbreviate that MOL, I know real short, right, equals 6.022 times 10 to the 23rd. We're going to go with 4 significant figures in this class. So if we do this with unit analysis, we'll say that there's 4.48 moles. And we'll say that we have 6.022 times 10 to the 23rd atoms in 1 mole. Those are going to cancel out. And then our final answer will have the same amount of sig figs as the moles that were given to us. Okay, and let's take a look at what that answer should be. Okay, we should be coming up with 2.70 times 10 to the 24th iron atoms. So a large, large number. Oh, all right. Molar mass. All right, let's get a definition for molar mass. The molar mass is the mass in grams of 1 mole of substance. We had this in the previous slide where we had all 5 of the different substances on the slide and we showed the different masses. That mass can be referred to in 2 different ways. We've called it the atomic mass before. And we can also call it the molar mass. And the molar mass is going to be the one that's a lot easier to work with. So for nitrogen, for instance, if we look at the periodic table, nitrogen is 14.01, and we can call it grams per mole. That's the unit. Very, very often used unit. You're going to use this unit a ton throughout this next year. So that means 1 mole of that substance has a mass of 14.01 grams. How about the molar mass of water? Well, that's 18.02 grams per mole. And you might ask, where did we get that from? Well, you add up the masses of each of the elements in the molecule. We've got 2 hydrogens at 1.008 grams apiece. And we've got 1 oxygen at 16.00 grams to give 18.02. What about barium nitrate? Okay, barium nitrate's 261.35. The math gets a little bit more complicated, but it's still addition and multiplication. Molar mass is big. So if I were to ask you which one of these 3 molecules or formula units would be the largest, well, you would say that it would be this last one, the barium nitrate. Okay, because it's got the most mass per mole. Let me ask you this. Which of the following is closest to the average mass of 1 atom of copper? Do you think 1 atom of copper is 63.55, 52, 58.93, or 65.38, or this really small number on the bottom? Now remember, we're talking about 1 atom of copper, and it should have come out to the number on the bottom, letter E. Okay? And you see that that's a very inconvenient number. It'd be very difficult to mass that on a scale. That's why the mole is so useful, because it allows us to mass out a number of atoms that we can reference. Let's calculate the number of copper atoms in a certain mass of copper, 63.55 grams sample of copper. So let's think about this. Do we have any conversion unit that would take us right from grams, right from grams to atoms? We don't. But the mole always acts as our intermediate. Do we know how many grams are in 1 mole of copper? Sure, the periodic table tells us. And do we know how many atoms are in 1 mole of anything? Sure, that's Avogadro's number. So let's do the math. Start with the number given, 63.55 grams over 1. We want grams to go away, so that's going to end up on the bottom. We said that moles is our intermediate. Let's put that on top. Now what should that number be? Well, that should be the molar mass for copper, and that is 63.55 grams in 1 mole. Grams will cancel out, and if you do your math right, the number would cancel out as well. And then we have Avogadro's number here on top. 23rd atoms for 1 mole. Moles cancels out. So your answer then is, in fact, Avogadro's number, 6.022 times 10 to the 23rd copper atoms. All right, lastly. So now we know kind of how to calculate the masses of atoms in a particular sample of substance. Let's say we've got a larger molecule or a formula unit. We had the barium nitrate in the previous example. And we want to know, well, okay, how much of this stuff is actually iron or barium? My example is going to be an iron compound here. We're going to call it iron 3 oxide. So take a look at iron 3 oxide, and we might want to say, okay, how much iron is there in iron 3 oxide? Well, now that we know this idea of molar mass, we can figure this out. Right? If we can write the formula correctly, Fe2O3, we know that there's 2 iron atoms and 3 oxygen atoms in one formula unit of iron oxide. So to find the mass percent, we're just going to multiply the molar mass of the element in question by the number of atoms in one formula unit and divide that by the total molar mass of the formula unit in question. So down here, if you're wondering, well, where did this come from down here? That is the molar mass of this whole thing, 2 iron atoms and 3 oxygen atoms. You're going to get a decimal number. We're going to multiply that by 100, and then eventually you'll get a percentage, 69.94%. Okay? So that's going to actually lead us into our next lab. And our next lab is going to focus on trying to find the amount of copper in brass. Okay? All right. There we go.